Okay, well, welcome back, everybody. Um, I will have everything graded as far as the grade is concerned, exam number 2 by this weekend. So give me a little time. There's about 4 or 5 questions I need to answer for each one. So I got about 75 questions times 5. All right, so give me a little time. I'll get those done for sure this weekend for you. We are on chapter 7. Things now seem to be kind of leveling out a little bit schedule wise. We're not so, hopefully not so jamming up all the chapters. For example, today this is the activity 25th, correct? And so we have activity number 7, or no, activity number from chapter 7, and homework due on Saturday and Monday respectively. After that, things get to be spread out. So anyway, let me start with chapter 7. And first of all, are there any questions, comments, concerns anybody has? Okay. According to my notes, this is where we ended up. We ended up on page 19. What we're doing here is one, so far we have been just kind of put everything together. We will eventually, that's my attempt, is to put everything together for you at the end so we can start looking at chemistry and how it functions and plays a big role in your life. Anyway, we talked about the elements, right? From the elements, we talked about these elements, how the electrons are put together and how the valence electrons, how many each one has with respect to the A elements, okay? The Roman numeral 1 through Roman numeral 8A. We know how many valence electrons they have. Now, the other guys, the Bs, we can't predict that as much. So we can't really do any prediction there. But we still know how many are in there, and we'll learn about that as we progress. So with that information, with the valence electrons, we first talked about Lewis dot structures for the atoms. Now, these are only for the A elements again. And those dots represented how many electrons there were, valence electrons for those atoms. Now we started putting compounds together. We started to learn how things are structurally bonded to each other, specifically the covalent bonds. Because the ionic bonds, the ionic compounds, they don't have a true bond. They just have an attraction, full-fledged negative, full-fledged positive attraction. Okay. And so we got into drawing these structures. We used the shapes table because with the shapes table, we're able to determine the geometry of the compound. And so with the valence electrons from every atom, we added them up. And then from there, we told you what the central atom was, and we came up with these structures. And we went through each one. Now, what the next slide does is just a rehash of what we did. And they're going to specifically take the HCN example. Okay. You'll always be given the central atom. They always be told to be underscored, it will be in bold. But in this case, hydrogen cyanide is the name of this material, is the carbon is the central atom, which tells you that the hydrogen and the nitrogen are bonded to them by some manner. At least, here's the key important part, at least a single bond. You know that part, that much so far. Okay. And so we start counting up all the valence electrons that every atom brings to the table. Hydrogen brings 1, carbon brings 4. And we know that. Why? Because we go to the group number that they're in. Hydrogen is in group 1. It has 1 valence electron. Carbon's in group 4. Has 4 valence electron. And nitrogen's in group 5A, which has 5 valence electrons. Remember, it is the valence electrons. That's where all the action is happening. That's where all the chemistry occurs, the outermost shell of electrons. So the innermost are full. Okay, they're not going to do anything. They're full. They're happy with their octet and, and so forth for that. That's it. So that's where the action's happening in the outermost shell. So now when you add up the valence electrons, point number 1, you always have a number divisible by 10. Excuse me, divisible by 2. what was I thinking? I know what I was thinking. I was adding up the valence electrons there, 10. But you always get a number that is divisible by 2. If you end up with an odd number, like 9, 7, there's a problem. Okay, check the group number to make sure you did your math right, and make sure you're using this correct number of valence electrons. So here we have a total of 10 valence electrons, of which I just divide by 2 to give me a pair. That way I can just simply make a line. I can keep track of that much better. Now you don't have to do that. You can make dots to represent each one of those electrons, and that's fine. Whatever makes you happy, and you can keep track of it. But I like the lines. Okay, doesn't mean it's right or wrong. It's my preference. Also, when I divide by 2, if I can't divide by 2, then I know there's a number problem. So it sends you back to the valence electron step to find out where that problem was. All right, so the fact that the formula is given, HCN is given, tells you that hydrogen and nitrogen are automatically bonded to the carbon, okay? Automatically, you know that. So you can very quickly draw that. And so I can quickly draw carbon, nitrogen, and hydrogen right there. Okay, so that takes care of 2 pairs. All right, I have 5 pairs to work with. And so now I have 3 pairs left, and I got to put them someplace. And you can put them anywhere you want. Now, can I put them on the hydrogen? I cannot. Why? Because the hydrogen, remember, has a duet rule. So I cannot put any more on the hydrogen. Here's a question. Shoot. Okay, yeah. You got, you said 2, Samira. 2 hydrogens, that's correct. Hydrogen can only.
I meant like you can't add more for the hydrogen. There's only 2 and 2's happy. It's enough.
Exactly. And so right here is a point, it's maxed out. That means that the other 3 I got left, I can put them anywhere else. I have to put them on the other atoms other than hydrogen. Now, I prefer to just put them on the outside elements right now. Doesn't mean it's the right way. That's my preference. And so I put 1 right there, 1 right there, and 1 right there. Okay? And you put them on the carbon if you want. 2 on the carbon, 1 on the nitrogen. It makes no difference, because eventually the next step is you got to look for the octet. Okay? Now, first of all, before you go any further, check to make sure that you still have, oh boy, I erased everything here by accident. Check that you still have 5 pair. 1, 2, 3, 4, 5. 3 yellows and 2 reds. Okay, which is what we calculated, 5 pair. Now, if you want the dots, do the dots. You're more than welcome to do the dots. You are not incorrect if you went this route. Oh, 2 dots. Okay, etc., etc. That is not incorrect to do that. But see, notice there's a lot of dots to be working with. Okay. Yes, you can rejoin on the phone. Go ahead. So you may need to pop out, Brian, and then come back in with your phone. Not a problem. Sometimes it's a little tough to read on the phone, but at least you can listen in. That'd be great. Also, I'm recording this, so you can also at the end view it again when your internet becomes more stable. Okay, so here we are. Okay, so here we are. Either put the dots or the lines, and like I said, with the dots, you can easily lose dots, and I just use the lines. Now, double check, make sure we got 5, and that we do. Let me erase all this here so we won't get it all mixed up. Okay. All right, so we still have 5. Now we check the octet, making sure everybody's happy. We can see that nitrogen has 80 electrons around it. 3 of them are not bonded. One pair is bonded. Okay, so there's a total of 8 electrons around it. Carbon only has 2 pair. So it's shy by 4 electrons, correct? So this is where you start making double bonds and triple bonds. Remember, that's the most you can make, triple bonds. There's no such thing as a quadruple bond, okay? Single, double, and triple. And so you can do is simply just take this pair right here and this pair right here and borrow from Peter to give to Paul, so to speak, and create a double bond. And by doing that, you end up with a triple bond as so. Okay. Now, do I still have 5? Yes, I do. Let me erase this one right here. Do I still have 5 pair? Yes, I do. I still have 5 pair. I haven't lost anything because you always do a check, make sure everything's okay, because this you can lose a pair as you're making the structure. And by losing a pair, you may end up with shy a pair. So keep track every step. Do I still have 5 pair or 10 valence electrons total? And sure enough, I have it. Check the octet. There's still 8 around nitrogen. 8 valence, 8 electrons. 3 pair or 6 of them are being shared with the carbon. Okay, they're being shared. So, right here, those triple bonds, those 6 electrons are being shared by the carbon and the nitrogen, totally being shared. So they can count for the carbon and the nitrogen as you count them. So around the nitrogen, look at the nitrogen all by itself, forget about what's bonded, and count the number of electrons around the carbon, and there's 8. Do the same for carbon, and there's 8. So everybody, and hydrogen obviously has the duet. So everybody's happy. I still got 5 pair. That is my structure. Okay. And that is my structure. A lot of times people have the challenge of when they're looking at the octet. So that's why I said, look at the carbon by itself, forget what's bonded to it, and just count the bonds around carbon. And you'll see there's 8, and do the same for nitrogen. And just remember that the triple bond is being shared, just like on the other side of carbon. On the other side of carbon, right here, okay, that is being shared. That bond is being shared. That bond is being shared with the carbon and the hydrogen, okay? So carbon is sharing with the hydrogen and the nitrogen. Now we're going to learn that that sharing is not equal. It's unequal sharing, but it's sharing nevertheless. All right, so we end up as follows. We make double and triple bonds as needed, and there's our formula. Essentially, that's what we did. Excuse me. Now, we're going to look at the Lewis-Dot structures for polyatomic ions. Now, what are those? Well, I direct you to, well, maybe not. Hold on one second. I lost my, give me a second. I lost my chemistry. Here we go. Okay, one more. Okay, we're good to go now. Now, on the periodic table, on the bottom left side corner, there is a table. and it's labeled most common polyatomic ions. Okay, I mentioned that a long time ago. I said we're going to use these a lot, and sure enough, here we are. Okay, now polyatomic ions. These are components or units that come together. They're not separated. They come together as one unit. Okay, so we have something called, for example, in the top left corner called ammonia. Now, notice something about all of these polyatomic ions, the term ions. That means they have a charge. So this ion has a positive charge. The ammonium ion has a positive charge. The other ones have acetate. That acetate is used quite a bit as additive. Next time you're reading the label, look at, you might find something called potassium acetate or something acetate. You would be surprised how much of this you eat. Okay, here's another one, hydroxide. Also, if you read some of your labels for, they've used this quite a bit in makeup and creams and solutions, you'll find a hydroxide. It does very well to actually destroy skin. It does. I'll talk about that later on. So anyway, these are units. Okay, these are units that come together. They're ions and they have a charge. If we ever need to have more than one unit, this is where we use that parentheses. Remember way back when we were talking about using parentheses around these units. Okay, so we're going to look at the Lewis dot structure of these polyatomic units. We're going to do the steps the same way, count the valence electrons. The only difference is this, is we're going to determine by its charge, we're going to either add an electron or subtract an electron. And you can see that most of the polyatomic ions that we use are anions, or negative charge. We only got one positive one here that we'll be using. Okay, so it's kind of easy to remember. There's one down here, down at the bottom. Next time you make chocolate chip cookies and you put baking soda, sodium bicarbonate, that's what you're putting in there, HCO3. Or if you use Alka-Seltzer, you have some of that in your tablets. Okay, and so that's what we're going to talk about, the polyatomic ions. Same steps, but we take into account the charge. Then finally, when we write the structure, we put a bracket around the whole structure and then the charge in the top right of the bracket. Not a parentheses, but a bracket. You'll see here in a second what I mean. And so if the ion, the polyatomic ion, is a negative charge, we're going to add more electrons. We're going to add depending on the charge. If it's a -1, we add 1. If it's a -3, we add 3. Okay? So if it's an anion, we add charge, an electron to it. If it's a cation, we subtract an electron. Okay? And then we put brackets around the whole picture with the charge, and we put the charge in the upper right. Okay. So for example, let's try the ammonium. That was a polyatomic ion, ammonium. Notice nitrogen is the central atom. Okay. And it has 4 hydrogens bonded around that nitrogen. So nitrogen, and I may have mentioned this, but if I didn't, I'll do it again. Normally, 99% of the time when you see a formula written out, 99% of the time, the first element is the central atom. So if it's not given to you, you can probably assume pretty good that the first element is the central element. All right. So we do what we've done before. We have 1 nitrogen. It comes from group 5. Okay, so we have 5 valence electrons. Then we have 4 hydrogens from group 1, bringing in 4 electrons. Now, if we were to stop right there, we have 5 plus 9, 5 plus 4 gave you 9, and that should be a flag. Whoa, wait a minute. I got 9 here. What's going on? So you go back and check to make sure it's in the right group. They're in the right group. So the numbers are good, but you're still getting 9. So what is the next thing you check? Oh, we must be talking about polyatomic ions. And go back, and sure enough, it's got a positive charge. That means I subtract 1 electron. So I now have 8 electrons, okay? Or 4 pair. 8 electrons. And I can very quickly, once I know that, let me put the thing, knowing that I can write nitrogen, and then very quickly put my 4 hydrogens there, like so. Okay. And guess what? 1, 2, 3, 4. That took care of my 4 pair. And now I spawned it. Now I can go write my bracket. I write a bracket over the whole thing. My next picture is a lot more accurate. And I draw it there. And there I am with my plus charge in the top right corner. Okay. There. And there's that bracket. Now I can also use my shapes table. So the question may be, well, what is the shape, the geometry of that polyatomic ion? And so here we use the same general formula that we did with the others, and we have A, B in subscript 4, AB4. Okay. Same process as the non-ions. So we go to AB4, we go to the shapes table, and the shapes table tells us that we have tetrahedral AB4 from the general formula. Tetrahedral, the bond angle is 109.5. So you can imagine now that if we were to draw this, I don't know if I can do it with my pen. So this would be hydrogen, 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 and then nitrogen right in the middle. 3-dimensionally, if you can imagine that, where we got 2 of the hydrogens in the plane, 1 hydrogen going back of the plane of the 2-dimension you're viewing, and 1 coming up forward. Okay, tetrahedral. One of the most common shapes that compounds have. Okay, so that's how we do the Lewis dot structure for polyatomic ions. No different from the other non-ions, except 2 things. 1, we either add or subtract electrons depending on the charge, and then we put a bracket around the structure with the charge in the top right. Okay. All right. Oh, it's not. Good question. It's not that you're losing. You don't have to determine which atom is going to lose it. What is actually happening here is normally, if we take one of these hydrogens, off, let me see if I can draw it. We get ammonia. Okay, the formula is ammonia. It's a good question. Let me bring this up. So if I put nitrogen and then hydrogen, 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 and then if we do a Lewis dot structure, we end up with a lone pair on that nitrogen. That's neutral. That's not charged. Now, here's the thing. I want you to think about this for a moment. We get a hydrogen that has lost that electron. Okay, hydrogen is in group 1. It lost that electron. Okay, and so here comes hydrogen. And that orbit, that 1s1 is empty. Okay, it lost its electron and it's got a plus charge, just like everybody in group 1. Everybody in group 1 has 1 valence electron. When they lose that electron, everybody in group 1 has a +1 charge. Hydrogen's no different. Okay, because hydrogen has 1 electron one valence electron. It's only got one. It can lose that. That one orbital in the electron configuration, 1s1, is now empty. Guess what? It's still there, okay? But it's empty. Nitrogen has two lone pairs here, okay? And hydrogen can come right in with that empty orbital and tie up those lone pairs on the nitrogen of ammonia. The result is this polyatomic ion with the plus charge. Those, when ammonia was neutral, those lone pair were on there. Now they're tied up with that proton. And so because they're tied up, we have to subtract one electron from the total amount of electrons that ammonia brought in, 4 hydrogens brought in, and 1 nitrogen brought in, okay? The opposite is true with the anions that we're going to do here. So it's not a matter of actually losing when we talk about ions. And when we talk about ions, it's a matter of those electrons that were there are tied up. And when they're tied up, they're still there, but they're not in the normal neutral stage. They now have a positive charge. So the ammonia is what we call the salt. Let me clear this up a little bit. The ammonia is the ammonium ion originally came from ammonia, and it tied up a proton or a hydrogen plus. And therefore, because it tied up, that lone pair now has a positive charge. The whole molecule has a positive charge. So we have to subtract one. And the same is going to be true. We're going to do an example of the anions and how we got to add an electron because there's extra electrons that are necessary. Okay. So it's not a true losing or gaining electrons. Yes, it's a matter of bookkeeping our electrons. Yeah, hopefully that answered. Okay. All right, so let's do an anion, for example. So here you can see for cations, normally the base compound has a lone pair, and then that lone pair is tied up. All right, let's take a anion. Now, what we have here is a species, it's a polyatomic ion. It's a very special one, actually. You normally think of bromide by itself, but bromide has the ability, when it combines with oxygens, to form this particular polyatomic ion. Okay, a bromate, but the name's not important right now. But bromine is the central atom, and we have 3 oxygens around it. And the overall charge of that is a -1, okay? And we do the same thing. We do the process. We count up the electrons. We got 1 bromine. It's in group 7, so 7 electrons, okay? Has 3 oxygens, all right? So 3 oxygens in group 6 is 18. Now, the fact it's got an overall negative charge, it has an extra electron in the whole system. So we got to account for it, okay? And we add 1 electron because there's a -1. With the cations, those lone pairs are tied up. And so we have to account for the other atom coming in here to tie those up. So we subtract 1. Here, we have extra electrons, actually, okay? And we have to account for that, so we add 1. Okay, and so our total now is 26 electrons or 13. Okay, again, if you didn't account for the 1 electron, you would end up with 25, which is a number not divisible by 2. So that would have been a problem. So you have to go back and check your bookkeeping. All right. And so we got 13 pairs. At this point, we do what we've been doing. Okay, nothing different. The bromine is the central atom. So I can very quickly, let me go down here. Bromine's in the central atom, and then very quickly write my 3 oxygens. Okay. That takes care of 3 pair. Now I got 10 pair to work with. Now, where you put them makes no difference, but you keep track of the fact that you got to maintain the octet. I prefer to start in outside atoms, fill up their octet, and move on to the next one and keep going. So I'm going to just start here and I go, all right, I got 10 pair to work with. So I'm going to take care of 1, 2, and 3. I stopped 3 because there's 8 now around the around this oxygen. So I move on to the next one. That's 3. So I got 4, 5, and 6. Again, I stop here because now I got 8 around that oxygen. So I got 6, 7, 8, and 9. Okay, so now I've taken care of 9. Then I got 11, 12, 9, 10, 11, 12. I have taken care of 12 electron pair. I calculated 13. Okay. I cannot put them on oxygen anymore because the oxygens are all full. So the only logical place would be on the central bromine. Okay. And so now I go back, do I still have 13? Count all my lines. I have 13 lines or 13 pairs. Okay. And now I put the bracket and I put a -1, and that is my structure. My general formula is this: A, B, 3, E, right? A represents the bromine, B3 represents the 3 atoms, the 3 oxygens, and E is my lone pair on the central atom, okay? And so I can use a shape table like I normally would, go to the shape table, and if I'm asked what that structure is, I look for AB3 and its trigonal pyramid. And here it is. I got the central atom, Br would be in the middle, the 3 oxygens, and then that lone pair. And so there's my structure. Okay. Now, the next one is SO3. SO3 is another polyatomic ion, and you'll be surprised. Here's SO3. Not to be confused with sulfide, SUFIDE. Sulfide is the sulfur ion by itself, okay? The S-2 ion. The sulfate, ATE, has 4 oxygens bonded around it. The sulfite ion has 3 oxygens bonded around the sulfate. Okay? Not to be confused with, let me make sure we understand this here. Sulfur, -2, that's the sulfide. Sulfide, that is the actual element that's in group 6. Okay, group 6 picks up 2 electrons all by itself, becomes sulfur with a -2 charge, just like oxygen. But when sulfur gets combined with 4 oxygens and has a -2 charge over the whole unit to make a polyatomic unit, it becomes sulfate. Okay, right here, sulfate. And next time you read a label, you'll be surprised how much sulfate you eat and all the additives and so forth that go in. Sulfites right here. You find a lot of sulfates in wine. If people drink wine, they get a headache beforehand. It's probably because the sulfites are constrictors, vasoconstrictors, and cause you to get a headache. And I mean, not a headache because you drank 10 gallons, but a headache in the beginning. Yeah, I don't mean the day after headache. That could be too, but anyway. So we're going to deal with the sulfates as a -2 charge. Similar scenario. We count sulfurs in group 6, 6 electrons. There's 4 oxygens. Okay, 4 oxygens. They're also in group 6. So I got 24 oxygens to work with. Okay. Then it's a -2 charge, so I need to add 2 more electrons. And so now what I have is 32 valence electrons. This is why I use the line, because that's a lot of dots to be hitting there and lose track. Or 16 pair. Okay. And so I know that sulfur, I've been told, is the middle element. So I can very quickly write sulfur. And then I got 4 oxygens bonded around it. Okay. So that took care of 4 pair of electrons. And so 32 minus 4 gives me what do I got left? Or 16, excuse me. 16 minus 4. I was looking at 32 pair. 32 pairs, 32 valence electrons, or 16 pair. I start out with 16 pair. I just took care of 4 pair. What do I got left? 12, right? Now, can I put any more on sulfur? I cannot. Why? Sulfur is full. I got 8 electrons around sulfur already. And so the only place I can put them are in the oxygens. There's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, that's 12 around the oxygens, 12, 13, 14, 15, 16. I got 16 pair all the way around. Okay, and this is a polyatomic ion, so I put my bracket and then my -2 out here. Okay, now I look at my general formula. Guess what? A, B, 4. And if I look that up in the shapes table, that polyatomic ion has an AB4 general formula or tetrahedral with the bond angles all around at 109.5. Okay. And so let me clear this and bring in a better picture. There it is. Okay. Note the bracket. Finally, over here we got carbon and nitrogen with a negative charge, similar to the hydrogen. Okay. Now, if you recall the HCN that we did way back when, we had, let me see if I can draw that real quick. We had HCN. Okay. Remember that formula we did? Now, if I take that proton out, that hydrogen, and leave that lone pair of electrons on there, I end up with a negative charge on the carbon. Okay. Negative charge. That's where the negative comes in by removing that. Anyway, we do the same thing. Carbon is 4 valence electrons. Nitrogen is 5. Okay. And then it's a negative charge. So we end up with adding an electron. So we get total of 10 electrons or 5 pair. And so we do what we've been doing. Okay. I can very quickly, there's no really central atom here because there's only 2. Okay. And so right now you can tell right away, as far as the structure is concerned, this is a linear structure. So that takes care of 1. And that means I got 4 left. Where do you want to put them? Put wherever you want. That's 2, 3, 4. Let's go right here. 5. So I got 1, 2, 3, 4, 5 pair. Okay. Then I check the octet. Guess what? Just like we did HCN, we got to make a triple bond. Okay. Because we're gonna take, because we got 8 on nitrogen, but right now there's only 4 on carbon. So just like we did in HCN, we're gonna make borrow from Peter to give to Paul. share them, that is, and we're going to make a triple bond to produce that. Okay. My partner over here is screaming. Anyway, that's the formula we get, HCN. Here's the question was one time, why does it have a negative charge? Remember, I mentioned a while back, this may help you. I said that if you look at the group that they're in, the elements that they're in, not only does it tell you the number of valence electrons, but it also tell you how many bonds it can make. Okay. Now, if you look at nitrogen, nitrogen is in group 5. Okay. When it becomes nitride, I said, when it picks up 3 electrons, it becomes nitride with a -3. So you know it needs 3 electrons for the octet. But what it also tells you as a side note that it can make 3 bonds when it's in a covalent. Okay. When it becomes ionic, it's going to have -3 electrons. But when it's covalent to make a bond, it's going to make 3 bonds. Look at that nitrogen. There's 3 bonds around that nitrogen. Okay. Now, if I were to tie up that lone pair on that nitrogen, it would be like ammonia. And now it will have a positive charge to it. Okay. Now, if you look at carbon, carbon is in group 4. I mentioned it can gain 4 or lose 4 as far when it becomes an anionic compound. But it also tells you it can make 4 bonds and be neutral. So when carbon makes 4 bonds all the way around, it's a neutral species. But as soon as whatever that species, whatever element is bonded to that one bond is removed, it picks up a negative charge. I drew HCN before, and that hydrogen was bonded to the carbon, but now it's not. So that lone pair is no longer tied up with the hydrogen, and that means that it's got a negative charge. Give me 1 second. My phone call is ringing. I need to find out who's calling. It's important. It's from the hospital. Hold on. Okay, I'm back. All right. So anyway, as I was saying here, where was I? Yes. So here's the structure for the cyanide. That is the polyatomic ion. Don't forget the brackets. We calculated 5 pairs. There's 5 pair of electrons around everything around the carbon. There's a total 5 pair. There's the octet has been fulfilled. So that's a legitimate structure there. Okay. Now, the thing about writing these Lewis dot structures is recognizing that one, if it's hydrogen, the max you can put on there is one pair of electrons. Everybody else has 8. Okay. All right. Well, this kind of brings us. Really, we should have. This should be reversed because I've been talking about this. How the electrons that are by themselves, they repel each other and they have a big effect on the structure. But I'll go ahead and follow suit the way they want us to talk about it. This thing is called valence shell electron pair repulsion, or VSEPR. And it just basically means, for example, that electrons have a negative charge. When they see other electrons, they're going to repel. The result is they're going to put themselves in a configuration that maximizes their position. Okay, they're not going to get closer together, obviously, because they're negative charge. The other aspect to remember is, we live in a three-dimensional world, so I'll be showing models of three-dimensional because that's what's going on, in the real life, so to speak. Okay, so we talked at length about the ABE general formula already. The A is the central atom, the B is whatever is bonded to the central atom, and E is the lone pair on the central atom. We don't care about lone pairs on other atoms, but on the central atom. And then the B and the E have a subscript which designate how many atoms are bonded or lone pair are bonded to the central atom. Okay. A lot of diatomic compounds that have no fear of ice cold beverage, they're very simple and straightforward. They're linear. You only have two atoms bonded together, and that's it. Okay, so we have chlorine, bromine, hydrogen, etc. Okay, now we have another example, the Ab2, that's also linear. A good example of that would be carbon dioxide. We're all familiar with carbon dioxide. We're going to come back and talk about carbon dioxide more at length here in a bit. But here, three-dimensionally, you can see that carbon represented in the black sphere, and then we get the 2 oxygens represented in the red color. Okay, a very linear structure. Another example would be the Ab3. Ab3, we have what's called trigonal planar. A good classic example of formula like this is something called formaldehyde. I'm sure you may have heard about formaldehyde someplace somewhere. I know they used to use it a lot as a preservative. If, like in high school, you are dissecting an animal like a pig or something, formaldehyde was utilized, but they're not using it so much now because it is a cancer-causing compound. So not a good thing to be using. So trigonal planar, central atom here is carbon, and then bonded around it are an oxygen and 2 hydrogens. That bond angle all around them is 120 degrees. Okay. The most common configuration found in nature is what we call the tetrahedral. And so here we have an example of methane. They got carbon with 4 hydrogens bonded around it, denoted by the three-dimensional model here. The black area, the black is the carbon, and obviously the white is the spheres, is the hydrogen. Remember that there is a pair of electrons being shared between the carbon and the hydrogen. So we got 2 electrons in every bond. They're negatively charged. So they're going to want to repel from the other bonds as much as possible. And when that happens, that's the configuration they come about. That's the most stable configuration that gives them the maximum repulsion from each other. Okay. Let me clear this up. All right. Another one's called the Ab2e Bent. Well, the reason it's bent is because of the lone pair that we end up with. Lone pair here on the sulfur. Now we may think this is linear like carbon dioxide in the previous example, but sulfur comes from has an extra pair of valence electrons coming in to the picture. And so that lone pair ends up in the central atom. Okay, and we end up with the Ab2e. Now, those lone pairs occupy a greater space than the ones that are bonded. So the result is that bond angle is reduced and shrunk in. So we end up with an angle much less than 120 degrees. Here's a good example of one here called sulfur dioxide. We'll come back to this one too. We're going to revisit this also. All right, and then ammonia, classic example for a trigonal pyramid, where we have a lone pair. After we add up all the valence electrons, we end up with a lone pair on the central atom. One thing about that lone pair on the central atom, whenever you end up with a lone pair in the central atom, just by default, you have what is called a polar molecule. Okay, we have two types of molecules. You're going to be polar or non-polar. You know, an example of something that's polar would be something that's water-like. Okay, an example of something that's non-polar would be something that's oil-like. We also know that oil and water do not mix, totally different properties here. All right, and so polar things, polar molecules will dissolve in polar solvents. Won't dissolve too much in non-polar solvents, but when you see a lone pair on the central atom, you can automatically show that it is going to be a polar molecule, and ammonia is a polar molecule. Again, here's a three-dimensional model sitting here with the lone pairs sitting up there. And because they take up more space, that bond angle, again, is much less than 109.5. All right, let's see. Classic example, here we go with water. We got two lone pairs, double the trouble, so to speak. Water is extremely polar. It's got two lone pairs on the central atom. So it's probably, yeah, it is the most polar solvent we have. There are some that are just a tad more, but water is the most polar solvent that we have. That bond angle between the two hydrogens, much, much less than 109.5. Again, because those lone pairs occupy a heck of a lot more space as compared to as if they were bonded. Much, much, much more space. So, given any covalent molecule or polyatomic ion, you should be able to hopefully draw the electronic dot structure or recognize what it should be. Okay. And from that, determine the shape and the bond angles, given the shapes sheet, the shapes table. So you might want to try for fun, practice is this formula, pH3. The phosphorus is the central atom. And you might try ozone. Here's for example, is the formula for ozone. Ozone has 3 molecules of oxygen, all bonded. One of these oxygens is the central atom. So try coming up and see if you can come up with a shape, okay, for PF3 and ozone. And then if you're still having trouble, we'll bring it to next class and we can go over it in the class. All right. So with that being said, we gotta talk about bond polarity. Okay. Now, we talked about covalent bonds and how that bond is either equally shared or not equally shared. Okay. If the atoms are the same in the covalent bond, then that bond is, those electrons are equally shared. Straightforward. If the two atoms in a covalent bond are the same, then we have a non-polar bond because those electrons are being shared equally. The other aspect is if the two atoms are different, guess what? Then you have a polar bond. Okay. The best way to look at it, and I think this is important because people have a tough time with this concept. Okay. But I want you to look at it this way. A bonded to A, non-polar bond. Okay, A and A are the same thing. Okay, A bonded to B, polar bond. Why? Because B is not the same as A and vice versa. Two different ones. And that's it. Okay. So you got to recognize what's being bonded and what you're looking at. If they're the same, they're nonpolar. Additionally, carbon and hydrogen, when they're bonded, it is nonpolar. That's the only other example. So that means that all of the diatomic compounds, hydrogen, chlorine, have no fear of ice cold beverage, and anything with a carbon hydrogen bond is a nonpolar bond. Okay, that means that everything else is a polar bond. That's it. And what do we mean by nonpolar? Well, it's polar because we end up with you could say the north and south pole, but we're going to talk about a partial negative side and a partial positive side. And that is related to the electronegativity. Okay. So equal sharing gives you nonpolar bonds. Unequal sharing gives you polar bonds. And that's all related to the electronegativity. And so the only thing to remember, carbon hydrogen is a nonpolar bond. Their electronegativity is essentially the same. So for all practical purposes, it's a diatomic molecule. Okay. Obviously, noble gases do not have any En values. They do not form bonds. Right. Remember that our benchmark was fluorine. Fluorine is on the top right corner of the periodic table. Fluorine is the most electronegative element that we have. And so when we compare the electronegativity of two different other elements in a bond, we look at it relative to fluorine because that tells us which is the most electronegative. Okay. And that tells us if there's a bond between two different elements, that tells us which of those two elements are pulling the electrons onto itself. Because remember, that is what electronegativity is all about. All right, so all the nonpolar bonds, all of the diatomic bonds, I should say, are nonpolar bonds. Have no fear of ice cold beverage. Included on that list is a carbon hydrogen bond, considered to be nonpolar because of the electronegativity of the two is essentially the same. Okay. Now, with respect to polar covalent bonds, it depends. Well, it's going to be polar because one of them has a higher electronegativity than the other. So some examples would be as follows: a carbon-oxygen bond, two different elements, right? AB, polar bond. A hydrogen and a chloride bond, two different elements, polar bond. Sulfur and chlorine, definitely polar bond, two different elements. Silicon and nitrogen, again, two different elements. Therefore, all of them are polar bonds, okay? All of them. Now, within the polar bonds, we are able to determine based on the electronegativity in which direction the electrons are being pulled. And so what we do is draw an arrow. We do two things. We have what's called a partial negative and a partial positive. This is the lowercase delta symbol. Okay, the Greek letter delta, lowercase. We have a delta positive and a delta negative. That means a partial, not a full-fledged negative charge like ionic compounds. They have a full-fledged negative charge. The partial means just a little bit of negative or a little bit of negative. We also draw an arrow with a plus mark on the end of it. The arrow part points to the most electronegative element. The plus part points to the least electronegative element in that bond, okay? And so here we have a carbon fluoride bond. Fluoride is a lot more electronegative than carbon, hence the arrow points in that direction from left to right. There is a partial negative charge on the fluoride because it is pulling those electrons to itself much greater than the carbon. Remember, we talked about the electronegativity that pull between them is like a tug of war competition. If I have two 200-pounders pulling the rope, we're essentially even Steven. Okay. Now I change one of those, and so we have a non-polar bond, two 200-pounders, they're the same strength, everything. I change one of those 200-pounders to a 400-pound puller. Okay. Now it's skewed. The pull is going to go toward the 400-pounder just virtue of its weight. Okay. Here, the pull goes to the most electronegative element. Now, these are called permanent dipoles because it's the nature of the beast. It is the nature of the beast that bond, because of the electronegativity, is going to have a partial positive and a partial negative. Without that, chemistry, as we know it, wouldn't function as far as making new compounds, because as an organic chemist, we rely on a polar bond so that we can make a reaction on that bond and create new products and so forth. If we look at the center example, we got an oxygen and the hydrogen. The polar bond, the arrow goes from right to left. There's a partial negative on the oxygen and a partial positive. Now you can imagine here that you got a partial positive and a partial negative. Guess what? Like magnets, wouldn't you expect them to maybe line up, interact with another CH bond by virtue of the partial positive and the partial negative to line up, and we have what's called intermolecular forces, all because of the partial positive and the partial negative. And the strength of that polarity gives us a lot of information, or tells us a lot about the properties of solutions. Okay. All right. So one last one is the phosphorus and the chloride. We have to determine, okay, which direction do we draw the arrow? Well, we're going to find out who is the more electronegative. We look at phosphorus, we look at chloride on the periodic table. We find that chloride is a lot closer to fluorine, right below fluorine. Therefore, it is a lot more electronegative. Now, all these elements have electronegative values, and people can go and memorize these numbers, and that's okay. But you can just use their position in our periodic table to determine who's more electronegative to help you decide which way that arrow goes, from left to right or right to left. Okay. So noble gases, we talked at length about it. They're not going to form anything. The octet is full. Okay. Fluorine is the electron hog. It's got the most electronegative of the elements. And that's why they use the idea of using fluoride in your toothpaste as they get incorporated in your teeth, the fluoride that is, they tend to form strong bonds. So that's why you use that. All right. Question here is, you have all these bonds. Right now we're just looking at the bonds. We're not even looking at the full molecule. But we're going to take the information in the bonds and we're going to apply it to the full molecule to tell us whether that molecule is polar or non-polar. So we have carbon, oxygen here. Okay. Oxygen is a lot more electronegative, so the arrow goes from left to right. There's a partial negative on the oxygen and a partial positive on the carbon. The next one, the nitrogen and fluoride, should be a no-brainer because we know the fluoride is the most electronegative, so the arrow goes from left to right here. Okay. Oxygen, hydrogen, we did that in this scenario. Arrow goes from right to left. Now, if it was written hydrogen bond oxygen, then the arrow obviously will go from left to right. The direction It could be right to left, left to right, but it depends on how it's printed. It's OH or HO, okay? Chloride to carbon, it's going from carbon to chloride with a partial negative on the chloride. And carbon hydrogen, no dipole. Remember, the electronegativity of the hydrogen and the carbon are essentially the same. Therefore, they're a non-polar bond. Okay, no polarity bond. Here you got three questions. Are these bonds ionic? And then which bonds that are not ionic, the covalent bonds, is it a polar covalent or is it a non-polar covalent? Well, the first one would be a lot easier, right? Because ionic, what is the criteria for an ionic bond? To refresh your memory, it has to be a combination of a metal and a non-metal. And so of these four choices, that is the only one that would be a ionic bond, because that's the only one with a combination of a metal and a non-metal. That infers that the rest of them are covalent bonds, which they are, okay? If we look at the first one, bromine is bromine bonded to bromine. The fact that the atoms are both the same should tell you I got a non-polar covalent bond here. Sure enough, because they're both the same atom. Okay, that's that example, A bonded to A. The other ones, B and F, phosphorus and fluoride, they're different, polar. Fluoride and bromide, they're different, again, polar, okay? And so the first example is a non-polar, and the other two examples are polar covalent bonds, okay? Now, once we know about polar covalent bonds, we're going to be able to identify the molecule, whether the molecule itself is polar molecule or non-polar, which then would tell us things. Would it dissolve more in water or would it dissolve more in oil? Things of that nature, okay? All right, let me clear this up. So polarity, it keeps coming. It will be coming a lot. So, we'll be using it over and over and over again. And just think of polarity with respect to the bonds as a tug of war between the bonded electrons. And the most electronegative element is going to win that tug of war, so to speak, and pull the electrons onto itself, much greater than the one that is least electronegative. They're not going to break apart like the ionic bonds. Remember, the ionic bonds have a full-fledged negative or positive charge. They attract to each other like two magnets, electrostatic attraction. Covalent bonds share electrons. Polar covalent bonds, one of them pulls more, is unequal sharing. And non-polar bonds are equal sharing, okay, of those electrons that are bonded. All right. Question here, ionic, polar, or non-polar bonds? Well, the very first one right off the bat, you got sodium chloride. And that's why it's important that you recognize the elements as to whether they're metal or non-metal. Why? Because a metal and a non-metal combine to form an ionic compound. Here we have sodium and chloride, metal and non-metal. We have an ionic bond, okay? Hydrochloric, hydrogen and chloride, two non-metals, okay? And two different non-metals together. Therefore, polar bond. H and H, two non-metals together. Furthermore, two of the same non-metals together. Therefore, you have a non-polar covalent bond. Chloride and carbon, two non-metals, covalent bond. They're different. Therefore, polar covalent bond. Carbon and hydrogen, just like the diatomic elements, they are the same. Okay, so they are non-polar covalent bonds. Oxygen, two of the same elements, non-polar. Potassium and oxygen, we got potassium, which is a metal, oxygen is a non-metal. We have an ionic bond. And then phosphorus and fluoride, obviously, we have a polar covalent bond. Okay. All right. So in general, you have nonpolar bonds. When you have all nonpolar bonds in your compound, you have nonpolar molecules. Okay. Now, if the polar bonds in your compound do not cancel out. Now, this is what we're using the arrow for. Okay, remember the arrow. The arrow designates a polar bond. There is a polar bond between that sulfur and oxygen. Okay. And there's a polar bond between the sulfur and the oxygen on the left-hand side. Notice the direction that the arrow points relative to each other. They are what we mean by canceling out. That arrow represents what is used, what is called in mathematics and physics is called a vector. A vector, simply put, is a something that has measurement and distance. If I say to you north, it doesn't mean anything. I know you can look north, but if I say to you 10 miles north, that is a vector. You know the distance, it has a magnitude, and you know the direction. Now, the thing about these arrows, and that's why it's important with it to determine which direction the arrows go to, is you can visually have them add or subtract each other, being vectors. So if I have an arrow going in this direction and another arrow, same magnitude in this direction, they're overall, they're additive. So I doubled the force, if you will, to the right direction. But if I take that arrow and I go one from left to right with the same distance, the length of the arrow kind of will represent the magnitude. So I'm doing my best to get them about the same. The other arrow, if I same magnitude approximately in the same direction, okay, the result is that the left arrow cancels out the right arrow. The net is 0 if the magnitude is the same, okay? I can do the same thing to be true if I went the other direction. One goes to the left, one goes to the right. Okay, the one in the left goes in the negative direction value. The one in the right goes in the positive direction value. Both of these here, in both cases, net equals 0. They cancel out. That one there for both of these. Okay, both not 0, 0. Okay, I only got about 3 more slides and it'll be done. So bear with me, almost in. So they cancel out. So what's happening here, one arrow goes to the far right, kind of southeast, if you will, and the other one goes to the left and down. Okay, so the dipole of each sulfur oxygen bond do not cancel out. So the polar bonds not canceling out results in having a polar molecule. Okay, now how does that relate to when they do cancel out? Well, carbon dioxide. Carbon and oxygen on the right-hand side have a polar bond. Carbon and oxygen on the left-hand side have a polar bond. The fact that the molecule is linear, and that's where the Lewis dot structure comes in, the fact that they're linear and they're going in opposite directions by the arrows, guess what? The dipole of each bond cancels each other out, and therefore we have a nonpolar molecule. That is why carbon dioxide in your carbonated drinks do not dissolve in water. They're in solution, but if you take a soda pop and you shake it, do you not cause all that carbon dioxide to come out? Because if they truly dissolved, shaking it would not decarbonate your drink. Okay, and that's due to the nonpolarity of the molecule. All right. I'm going to go just a little bit over, so bear with me so I can finish this chapter out. And so carbon, the first example, carbon and hydrogen, all nonpolar bonds, you can automatically assume we got a nonpolar molecule, okay? Remember all the carbon hydrogens. Now we had talked about the molecules canceling out. and you gave an example. But here's another example of bonds that can cancel out. If we take the tetrahedral, okay? If we take the tetrahedral and let's, for example, put chloride there. Okay. Oh, well, we got too many things going on. Uh-oh. Bear with me for a second. My mouse is acting up now. Okay. Let's take the tetrahedral. Mm. Mm. All right. Now, okay, maybe this will work this time. Nope. All right, let's do this. If in that tetrahedral we had 4 chlorides around it, had a chloride there, all the way around, carbon in the middle, we would have polar bonds there, right? The polar bond between the carbon and the chloride would be in 4 different directions. Okay. In the tetrahedral position, and if you have 4 polar bonds with the same magnitude, they will cancel out. And therefore, even though that's another example of the polar bonds canceling each other out, therefore we have a nonpolar species. Okay. And so even though methane, like we said, all nonpolar bonds, they would end up with a nonpolar molecule. If I were to replace all 4 of these hydrogens with chloride, they also have tetrahedral, but all those 4 bonds will cancel each other out. They will still continue to be nonpolar. But if I replace it, only one of those hydrogens with the chloride, I end up with 1 polar bond. It doesn't cancel out the other 3. So I end up with a polar molecule. So by playing with the structure, I can make something polar or nonpolar. Now, PF3, if we run through this example, you'll find that there's a lone pair in a phosphorus. Okay. And its structure would be, like we did with ammonia, it would be the Ab2e with trigonal pyramid. So the phosphorus could be in the center and the chlorides here on the edge. Those chlorides take up a lot of space. These 3 polar bonds would not cancel each other out, and we end up with a very polar species. Okay. And then carbon dioxide, we just talked about that. The fact that each one there is 2 polar bonds in that molecule, but they cancel each other out. Therefore, we end up with a nonpolar species. To try this out on water, H2O, and ammonia, NH3, try it out for yourself. Draw the Lewis dot structure, determine the shape, check out its bond angle, determine if the bonds are polar, and then determine if the overall molecule is polar or nonpolar. Okay, try that and see what you come up with. If you have a challenge with that, then we can talk about it on Tuesday. All right. Congratulations. You're done with chapter 7. Somebody who needs to say hello to you guys. She's over here screaming on the sideline. She's gotten used to coming in here. Let me stop the share for a moment. She's like, I want to see what's going on here, guys.